When I say design, you probably imagine patterns on a wall, drawings inside an art book, a logo, a chair, or something made to look beautiful. But that is only the smallest corner of design. Design is the act of taking chaos and forcing it into an order that serves a purpose. And everyone uses it. A child designs a shortcut to reach a shelf. A cook designs the order in which a meal is prepared. A programmer designs the flow of information. Science can tell us how electricity behaves, but design is what arranges billions of microscopic switches inside a chip and makes them work together without turning into a useless block of silicon. Design is what uses aerodynamics to turn metal, fuel, wires, and mathematics into an aircraft carrying hundreds of people through the sky. That is what engineering really is. So, in today's video, we're going to explore design, organization, and the principles behind every system powerful enough to conquer the world. Imagine that you are hungry. In front of you are vegetables, oil, spices, heat, utensils, and 30 minutes of time. None of these things is a meal. They only become a meal when someone decides what should happen first, what should happen next, which ingredients should be combined, and which ones should be kept apart. That arrangement is design. Now, replace the vegetables with people, the kitchen with a company, and the recipe with a workflow. The principle remains almost exactly the same. The economist and cognitive scientist Herbert Simon gave one of the broadest definitions of design. He argued that everyone designs when they create a course of action intended to change an existing situation into a preferred one. That means design begins with dissatisfaction. Something exists, but you want it to exist differently. You are on the ground, but you want to reach the roof. Information is everywhere, but understanding is not. People are separated, yet somehow they must act together. Noise is all around us until someone arranges it into music. The distance between what exists and what you want is the design problem. Design happens constantly, often without us noticing. Planning your morning is designing a sequence. Rewriting a sentence is designing information. A shop layout designs movement, and a film scene designs curiosity. The principle is always the same. You have a goal, limited resources, and real obstacles, so you arrange what you have to make the result possible. That is why constraints matter. Asking someone to build a bridge means nothing until you know the distance, weight, cost, materials, ground conditions, wind, and possible points of failure. Without constraints, there is no real design problem, only an idea. Design begins when reality refuses to give us everything we want, and cleverness is how we work around that. People often imagine engineering as complicated mathematics. And yes, engineering uses mathematics. But engineering is not simply calculating the correct answer. In real engineering, there is usually no single perfect answer. A stronger aircraft may become heavier. A lighter battery may store less energy. A safer building may become more expensive. NASA describes systems engineering as the art and science of creating an operable system while balancing requirements that are often opposed to one another. Different specialists must be balanced so that one part of the system does not destroy the rest. That balancing act is design. Good design is an intelligent compromise between competing demands. And sometimes the cleverest solution is removing what does not matter. Consider the London Underground map. A geographically accurate map of London shows the real distances, curves, and directions of the railway lines. That sounds useful, but for a passenger underground, most of that accuracy is irrelevant. You do not need to know the exact shape of the tunnel. You need to know where to enter, where to change lines, and how many stations remain before your destination. In 1931, Harry Beck developed a diagrammatic map that simplified geography and emphasized connections. The lines were cleaned into regular angles. The stations were spaced more consistently. and the network became easier to read. The design was initially unconventional, but it became an enduring model for transit maps around the world. Beck improved the map by making it less geographically accurate. He understood that accuracy and usefulness are not always the same thing. A good design does not show everything. It shows what matters for the task. Computer chips push this principle to an absurd scale. The Intel 4004, released in 1971, contained approximately 2,300 transistors on a single microprocessor. Those transistors were arranged into registers, control logic, an arithmetic unit, and pathways through which data could move. Today, advanced processors contain billions of transistors, but a pile of billions of transistors is not a computer, in the same way that a pile of bricks is not a city. The real achievement is the architecture. Which transistor controls which signal? Which operations happen first? Which sections communicate? Where is information stored? What happens when two instructions require the same resource? A processor works because an almost unimaginable number of tiny switches have been organized into layers of responsibility. At the lowest level, a transistor switches. Above that, gates perform logical operations. Groups of gates form functional units. Functional units form processors. Processors form computers. Computers form networks. And networks form much of modern civilization. At every layer, complexity is controlled by hiding unnecessary details from the layer above it. You do not need to understand the movement of electrons to edit a video. Your editing software does not need to know the shape of every transistor. Each layer performs its task and presents a simpler interface to the next. This gives us one of the most powerful principles in design. When a problem becomes too complicated to understand as one object, divide it into levels that can be understood separately. Design is the intelligence of knowing where those divisions should be. Creating one working object is difficult. Creating 1 million objects that work together is a completely different problem. At small scales, humans can depend on improvisation. 5 people can talk directly, but improvisation begins to collapse when a system grows. 5 people may need a conversation. 5,000 people need roles, schedules, records, procedures, and lines of authority. Scale demands organization. And one of the most powerful tools for creating scale is standardization. Take the shipping container. Before containerization, cargo could arrive at a port in sacks, barrels, wooden crates, and irregular packages. Each item might need to be handled separately. Different goods required different arrangements. Loading and unloading demanded large amounts of labor, time, and coordination. The standardized container changed the problem. Instead of redesigning the entire transport process around every product, the world could design ships, cranes, trucks, and trains around a common box. ISO formed a technical committee for freight containers in 1961, and later standardized details including dimensions, stacking systems, and the mechanisms used to secure containers during transport. ISO published its first freight container standard in 1968. The most important feature of the container is not simply that it holds objects. A cardboard box also holds objects. The container's power comes from being an interface. A factory does not need to redesign its goods for every ship. A crane does not need to understand what is inside. Each part of the system only needs to understand the standardized connection. That is how design allows complexity to scale. Walk into a building. Where do you move? Probably toward the doorway. Why? Because the building has already limited your possible movements. Stand inside a queue. Where do you wait? Between the barriers someone placed there. Open an application. Which button do you press? Probably the largest, brightest, or easiest one. Every designed environment contains suggestions. Some are gentle. Some are unavoidable. This is sometimes described as choice architecture. the structure of the environment in which decisions are made. Research in behavioral economics has shown that the way choices are arranged can influence what people select. Defaults are particularly powerful because many people remain with the option already selected unless they actively change it. These ideas became an important part of Richard Thaler's Nobel-recognized work in behavioral economics. A menu designs how you encounter food. A supermarket designs how you encounter products. A road designs how quickly drivers are encouraged to move. A social platform designs which actions require one tap and which require 6. This means design is never completely neutral. Every design makes some actions easier and others harder. A staircase makes climbing possible for one person while blocking another person using a wheelchair. A wide highway may shorten a commute while dividing a neighborhood. That is why bad design does not always look broken. Sometimes it is working exactly as intended. A complicated cancellation process may be badly designed for the customer, but very effectively designed for retaining revenue. This is what design is. It's everywhere, you just don't notice it, because that's what we call design, keeping you unintended and taking the benefit.